All right, let's move on to the next question. This is 2.21. So in here, we have a grid circuit. And the question is, we're trying to find all the voltages between any two nodes. So in here, I have V, M, N, the subscripts, experiencing that, well, given the voltage provided here, I should be able to find voltage across any two nodes. Before we look into the details, I'd like to kind of reiterate on two concepts for solving this problem. The first one will be KVL, the Kirchhoff voltage law. Kirchhoff voltage law states that for the voltage across a loop, we'll have an algebraic sum of 0. Well, this also brings us this idea of how can we identify loops. By definition, a loop is a closed path in a circuit that's without any repeating nodes or elements. Well, if you're looking at this grid network here, what you have is for any of the loops in this circuit, as long as there's no repeating elements, it can be considered as a loop, and then you can apply the Kirchhoff voltage law on top of this. There are some obvious loops. For example, each of these smaller grid will be one of the loops. For example, A, B, E, D will be one loop, E, F, I, H will be other. There are also other loops that is a little bit hidden, if you will. For example, this part can be another loop. A, B, C, F, E, H, G, D. This is another closed path without repeating elements. So after we kind of understand these two concepts, the voltage law as well as the idea of a loop, we can set out to solve the voltage across this network. So in this question, we have quite a few, it's listed quite a few of the different voltages it's want to find out. So here we're only going to do one or two examples to give you a feeling on how to solve this. For example, we're interested in finding VDA. So that is the voltage across this element. To solve this, you can apply KVL in various loops. However, before you do that, I'd like you to examine the circuit first. For example, an obvious choice of a loop will be this loop A, B, E, D, as we already know. But if you're looking at this, in this loop A, B, E, D, only the voltage across node AB is known. So writing the voltage law for this loop will not help much, because you end up with two more unknown variables. So can we find a better loop to solve this? Of course we can. And one option you have, you can focus on this outer loop, if you will. If you notice, across this loop, this A, B, C, F, I, H, G, D, you already know all the voltage across the edges. Then to get the voltage here, you just need to write out your voltage law across this loop. And we're going to do exact that. Well, here, notice when you apply KVL, you also need to have a reference direction for how would you examine the positive terminal of this voltage. And since we already wrote VDA here, we're going to assume traversing this loop in the clockwise direction, and the first part, or the first terminal we encountered, will be the reference positive terminal. So this is DA. So D is the positive, A is the negative. And then as long as we traverse this, we have, well, this 8 volt. Encounter the positive first. 12 volt, but here the reference direction is a negative value, so we have a negative 12. in this CF node, we have another positive, Fi positive, IH positive, and Hg. Notice here, if you're traversing this in this clockwise direction, the first terminal we encounter is -1. So this will be a -12. And again, GD voltage, again, we're encounter the -1 first. So this is negative, I'll write it here, -16. And we finish our loop. And adding this together, our result will be -6 volt. Well, let's try another one. In here, we might also interested in one of the questions is asking us what will be the voltage across the node GC. So notice here, voltage GC is actually this one. So G is the positive terminal, and C is the -1. So in here, what we can do is that this is a conceptual loop rather than a physically connected one. But even for these conceptual loops, we can still apply KVL. And in here, if we're going to assume our reference direction is still in this clockwise direction. So assuming we're going to examine this loop in this way, right, clockwise. What we can have is, well, VGC, G being the positive terminal, coming to this element here, we have positive 20. Again, positive 14. Here, positive 4. When we're reaching here, this starts with a negative terminal. This is -12. And the algebraic sum is 0. Right? You'll notice here, the conceptual loop I choose is this one, GCFIH, right? This triangle shape element. The reason I'm choosing this this loop again is because based on our observation, there's only one unknown value in this loop, which is the GC. And with this known values, we can easily solve what will be the VGC across our terminals. And in this case, VGC will be a negative voltage of 26.